Hello everyone, and welcome to another CryoSPARC tutorial. This time I'm going to be covering an in-detail procedure for creating a mesh, and these meshes are used for 3D flexible refinement. This is an exciting new or relatively new technique in CryoSPARC, but it has this additional constraint of the mesh. And so today I'm going to go into a bit of an introduction as to why we need a mesh for 3D flexible refinement. I'm going to talk about kind of what that mesh does. Then I'll discuss what you need to do to prepare to create one of these meshes. I'll walk step by step through the process of performing a segmentation as well as using that segmentation to create a mesh. And then I'll talk about some potential pitfalls and things to watch out for when you're sort of fine-tuning your mesh and things you might want to, settings you might want to play with to get the best possible result for your 3D flexible refinement. So without further ado, let's go ahead and get started. I'm going to start by talking about what is the goal of 3D flexible refinement. What are we actually trying to do here? And the answer to that question, perhaps obviously, is that we know that these proteins are flexible, or that our targets are flexible, right? They are not perfectly rigid, stationary objects. And so the goal of 3D flexible refinement is to model that flexibility. 3D flexible refinement directly models per particle deformations. And the goal is that we can reverse these deformations to improve our consensus refinement using the information that we've learned about how these particles are flexing. So for instance, if your particle has two domains that flex relative to each other, you could perform something like a local refinement to sort of independently resolve these domains. But the local refinement still requires that each of those domains are rigid internally. If one is still moving sort of within itself as well as in comparison or adjacent to this other domain, then the result of a local refinement will still not be so great. And something like 3D variability analysis will tell you that this is happening, right? You might be able to see the flexible motions of, say, an antibody that's bound to your target, but it won't let you recover any of that information. And so that's where 3D flexible refinement comes in. The idea here is that in addition to just modeling what types of variability exist, because we are directly modeling the deformations in 3 dimensions, we are able to sort of undo those deformations and recover a consensus map that is also this sort of undeformed map by moving density back where it would be if that particle hadn't flexed. That's why we need a mesh. Okay, because if we tried to directly model the movement of voxels around, right, if we tried to say this much density from this voxel should actually be over in this voxel, there would be far too much noise in our images. Because remember, ultimately, we're always talking about images, and our images in cryo-EM are very noisy. And so there would be far too much noise in our images for us to successfully model the deformations that we need to in order for this technique to work. So instead, we create a mesh. And these meshes are a set of tetrahedrons that tile the entire three-dimensional space that our volume occupies, okay? And when we instead model the deformation of these tetrahedra, we are only moving 4 points around, right? There's 1, 2, 3, 4 points for every tetrahedron. And when we move those points, we scale all of the volume density that's in that tetrahedron linearly. Okay, and so that means that just by modeling 4 points, we can actually move density around between a significant number of voxels. And in addition to reducing the degrees of freedom, and so sort of giving us more signal per thing we're trying to move around, it has an added benefit of imposing smoothness on these deformations. And when I say imposing smoothness, I both mean sort of the types of movement that are allowed, right? We're only allowing sort of these continuous deformations. But it also means that within a tetrahedron, right, we can't have things moving apart. The tetrahedron must sort of stay a single connected entity. And this is really good because we know that if we look at, say, an alpha helix, we don't want that alpha helix to just explode, right? If we ever think that that's what should be happening, that means that our model is overfitting noise. That's probably not what's actually happening in our protein. It's just all the residues blowing up and moving apart from each other. And so that's another nice thing that these mesh sort of constructs do, is they impose that that restriction that within a tetrahedron, we know that things aren't moving apart from each other. So that's why we need a mesh. But why do we need a custom mesh? If you just plug in the map and mask into CryoSPARC's 3D Flex Mesh Prep job, it will give you a mesh. It will be a bunch of tetrahedra that cover your entire target. And this works well for a lot of things, especially if there's sort of one solid object that just has some kind of internal flexibility. You need a custom mesh when you have domains that will flex past each other, that will either slip and slide adjacent to one another but not connected, or move apart from each other when there's solvent gaps between domains, essentially. And the reason you need this is that, recall, we don't allow the tetrahedra to sort of split things within themselves, right? The tetrahedra must keep everything inside them sort of connected. And so if you have a tetrahedron that spans a solvent-filled space, anything on either side of those solvent-filled spaces will have to stretch that tetrahedra to move apart from each other, which the model will treat as this kind of expensive thing, right? It doesn't want to have these really large deformations of the tetrahedra because, for all the model knows, there's an alpha helix in there, which we just said we don't want to explode in that way. And so in order to allow these solvent-filled spaces to expand and contract, we need to tell CryoSPARC that the things on either side of it are in fact independent, and they're allowed to move independently of each other. And that's what a custom mesh does. And you'll see how it does that once we've created one, but that's the goal here. If you have a single sort of continuous object without any things that slip and slide past each other, the sort of default mesh where everything is connected might be sufficient. The times that you really want to consider making a custom mesh are when you have domains that need to move sort of past each other or away from each other. Here on the screen, I have kind of an example of the minimal set of jobs that you need to start doing a 3D flexible refinement. And that is a flex data prep job and some kind of mask that you've created. You technically don't even need the mask. You could generate one directly from the volume, but we have found that your results will be much better if you use things that you know about the protein, where the solvent is mostly, to generate your own mask and then give that to the 3D flexible mesh prep job. The data prep job is pretty simple. All it does is it downsamples your particles to the appropriate size and does the same thing with the volume. This consensus volume is what we really care about, and this is what we'll ultimately use to create our 3D Flex mesh. But before we do that, I want to talk about one optional job that we really recommend you run if you're not in a big hurry or if you kind of haven't run it before, which is 3D variability analysis. There's a lot of information about 3D VA, which is what I'm going to call it from here on out, in the guide. And so I'm not going to go into too much detail about how it works and what it tells you. But the reason we recommend you run a 3D VA job is that it is another way of assessing flexible motion in your particle images. And the nice thing about it is it doesn't require a mesh. So it doesn't require you to come in and make these kind of assumptions that we're going to be talking about today when you generate a mesh, because it doesn't need a mesh. So I have run 3D variability analysis on this protein, and I forgot to say this is the sodium channel, the NAV 1.7, and I will link to the EMPIAR dataset in the description of this video. And so if we pull up the 3D variability analysis results here, I've got the three components. This is component 0, component 1, and component 2. And if you're not familiar with 3D VA results, you can just think of these components as types of motion, right? We're kind of trying to resolve the three major types of motion in these results. And the way this ion channel works is we've got the a terminal domain here, and then we have the main ion channel, which is in a micelle that you can't see right now because of the contour I've set. And then these are two fabs. Those are fragments of an antibody that bind the antigen. So this is just to sort of help orient and align the particle. These are not part of the channel, but we still would like to be able to resolve them, and they provide a good illustration of this technique. So if I play this volume series, you can see that the fabs are moving toward and away from each other, right? And we can actually see different types of fab flexing in each of the three modes. But in each of the three modes, these fabs are flexible. And that's not that surprising, right? These are independent proteins that are attached pretty far, that they're attached to the channel down here, so that they're not attached to each other at all. We can also see that the transmembrane domain of the ion channel here is sort of warping or flexing up and down. And whether that happens symmetrically or asymmetrically depends on the mode. And then finally, this terminal domain here, these long helices that stick down. In 3D variability analysis, you see these like appearance and disappearance. That's just a side effect of the technique. Really, what's probably happening is they're flexing back and forth. And so at the very distal edge, we just can't see them at this contour level. So why do we recommend that you run these 3D variability analysis jobs? Well, for one thing, it'll tell you that there's actually motion there, right? Before you invest all the time and energy in creating a 3D flex refinement mesh and then running the training job, which is pretty computationally expensive, it's good to verify to yourself that there is motion in your data set. And it also will tell you what kinds of motion you can expect to see, right? Now I know that I expect to see some kind of bending, I expect to see some kind of flexing of these helices, and I expect to see these fabs moving around. So the kind of things I would expect a priori in this case are actually in my data, according to 3D variability analysis. This is important when we generate the mesh, and you'll see why once we start making decisions about where to cut this mesh, and that's mostly what we're going to be talking about when we talk about generating a mesh. Let's start to talk about what we're going to do when we make a mesh. When we make a mesh, we are going to be telling CryoSPARC whether or not it should split the mesh into sub-regions. And I know that sounds like a lot, but if we just plug in our map into the 3D Flex Generate, it will put everything that is inside of our mask in the same mesh. And the reason that this matters is that, remember, we don't let things that are inside a tetrahedron move apart, okay? Everything that is within a tetrahedron must stay continuously attached. And we know that these fabs want to move apart from each other. And so the tetrahedra that are connecting these fabs, which may not be very many, it may only be 2 or 3 tetrahedra between the top lobes of these two fabs, they will have to stretch and compress as those fabs move away and away from each other and toward each other. And that is expensive in terms of the model, right? The model is trying to reduce how much stretching it does because we don't expect there to be these really, really large fluid motions. But here, there shouldn't be any penalty on really stretching this space apart because there's nothing in there to stretch, right? We know that that's just solvent in there, but the 3D flexible refinement model doesn't know that. And so in order to tell the 3D flexible refinement model that it's allowed to move this region apart, or another common thing, if we looked at this from the top, if this fab wants to move up and this left fab wants to move down, then these tetras would have to sort of stretch and skew in that way. But if we tell CryoSPARC that it's allowed to do that, right, that it's allowed to just slip these tetrahedra up and slip these ones down, then it doesn't have to pay for that cost of stretching and compressing those tetrahedra. So that's what we're trying to do when we create a custom 3D Flex mesh, is we're trying to allow these tetrahedra to stretch and slide past one another. And there's more illustration of this in the guide if you're not understanding. But basically the idea is we want to segment out any regions that we think will move independently of each other. So let me give a concrete example here. If we contour down a bit, we know that these helices flex back and forth. We know that this transmembrane domain is going to flex up and down at each of its extrema, but is probably relatively stable at the core. And we know that these fabs shouldn't be moving relative to the transmembrane domain, right? We know that they're attached here, but they might and probably do move back and forth relative to each other. So this is not an attachment point, okay? And one last thing is that the micelle, even though in reality it is this fluid object, in our images it looks like a relatively stationary, low-pass filtered blob. So it may not look like it's moving very much in our images, but we know that the transmembrane domain is moving a lot. And so what we're going to want to do is also segment out the micelle so that it can move sort of independently, or more likely not move independently of the transmembrane domain, which is moving. So those are the 4 segments that we want to create. We want to create the kind of core segment, or just kind of the ion channel segment, which is going to be the transmembrane domain in this terminus here. We want to create a micelle segment, and we probably want the transmembrane domain to be allowed to move relative to the micelle segment. And then we want to create 2 fab segments, one for each of the fabs we have. And the reason we want to segment out this way, just to be clear, is because we want those fabs to be allowed to move relative to each other, but not allowed to move relative to the transmembrane domain. So I'm going to use Segger, which you can find in Tools, Volume Data, and then Segment Map here. So then you can go ahead and click Segment. And here you can see it has broken our ion channel into these large, relatively coarse segments, which makes sense. It's a low resolution map. You can always Control click and then click Ungroup to start breaking things apart into smaller and smaller regions. And remember that we actually want our mask to cover the micelle. And the reason we want the mask to cover the micelle is that the micelle will be there in the images. And so if 3D Flexible Refinement doesn't know that the micelle is there because it's outside the mask, it's going to still try and fit it to the images, right? The images will have the micelle, and so it's going to try to move density from maybe our transmembrane domain helices into micelle density because it needs to explain that density somehow. And so this would actually not be a good segmentation because we want to see that micelle here. So what I'm going to do is reduce the contour of our map until I can see the micelle, and then click Segment again. And now you might be worried that you won't be able to see the helices, but if you come in here and click Ungroup a bunch and then hide, hide some of these outer segments, you can see that the helices are still in there. So if you hide all of these outer micelle segments, you should be able to end up with just the regions that we want to be able to slip past each other, right? You want the ion channel, the micelle, and the 2 fabs. I have covered how to use Segger in the mask creation video and guide page. So if you're not familiar with the tool, go and give those a quick view. And then I will put up my finished segmentation so that you can try and get yours to look kind of similar to this, at least for your own target. This is what my final segmentation looks like. And you can see, just as I described, I've got one segment that covers this right-hand fab, one segment that covers this left-hand fab, and of course, that's just in this view. It's just one fab in the other fab. I've got one segment here that covers the entire ion channel, right? Both the TMD and the sort of intracellular domain down here. And then I have another segment that I've put in mesh view just so that we can see the ion channel, which is the micelle. And it's got some holes in it, and it's not perfectly contiguous, but that's okay. Your segmentation doesn't have to be absolutely perfect because once we plug this segmentation into the mesh generate job, it will be expanded to fill the entirety of your mask. So as long as you get it, mostly correct, that will be sufficient for what we need to do. One thing I want to point out here is that you'll notice I did try to create as few segments as possible, right? In this example, we have only 4 segments. I could have just left the segmentation as is and then told CryoSPARC which segments I wanted to fuse to which other segments. But A, that creates a lot more work for you in sort of typing together these fusion parameters that we'll describe in a second. And also, it can cause some problems if the segments are especially small. So generally, we would recommend that you create your sort of segmentation segments that we'll upload to create the mesh to make them as big as possible while still retaining the relevant relative motions. So for instance, even though we could make this fab thing into one segment, that would sort of defeat the purpose because now these tetrahedra would be fused to each other. Now that I've finished my segmentation, I'm going to click File and then Save Segmentation As. And then I will just go to my desktop and call it example.seg. And then I will upload this to our CryoSPARC workspace, and we'll move over to a discussion of the actual job itself. Now we are back in the CryoSPARC workspace, and it's time to create our mesh. So the first thing to do is make sure that you've run the required jobs. Here we've got this flex data prep job, and then the import volumes job, which will give us a mask. I'm going to come over here and type mesh, and there's our 3D Flex mesh prep job. So you can see it's expecting a consensus volume and a solvent mask, and we've got both of those. So I'll go ahead and plug the volume in here. Note that we don't need the particles for this part. And then I will give it our mask as well. So what the mask is doing here is defining where the tetrahedra should exist. We don't want to put any tetrahedra where we think it's all just solvent, because that would just waste computation on modeling the random fluctuations of solvent. So the mask in this case will define the maximum extent of the tetrahedra that we are ultimately going to create in our mesh. You don't need to worry about any of these parameters if you've plugged in your own solvent mask, which again, I recommend that you do use your own custom-made solvent mask. And then here is the important set of parameters. So base num of tetra cells is telling you over the entire box how many tetrahedra should there be. So by default, it is set to 20. And that means that over the entire box, no matter how big the box is in pixels, right? In our case, the downsampled one is 126 by 126 by 126 pixels, and that will be covered by 20 tetrahedra. So each tetrahedron will be approximately, what is that? 6 voxels wide. And that works well for most data sets. Unless you have an extremely, extremely large pixel size, we really recommend keeping this base number of tetracells at the default of 20. And there's 2 reasons for that. One is the more tetracells you have, the more expensive that computation gets. And so adding more tetracells is going to make your training take longer, which is going to make kind of everything slower. The other reason is, as we discussed, these tetrahedra are large for a reason, right? We want them to be holding together the parts of the density that we think belong together. We want our trajectories, our deformations, to be smooth, spatially smooth. And so if you were to increase the number of tetracells, you're sort of breaking those parts that have to be smooth into smaller and smaller regions of your map until ultimately you'd be trying to move individual voxels again. And so that's why we really recommend keeping this around 20. Another heuristic we use is that a single tetrahedron should cover 1 to 2 alpha helices. That's not a hard and fast rule. Certainly other strategies probably work, but it's a good sort of starting point for thinking about whether or not you'd want to change these tetracells. But again, we really think 20 is kind of a good default parameter. Here is where we will plug in our segmentation file. So we can just go to my home directory, and we'll see I have the example.seg that I uploaded. So we'll select that. Segment connections is a really important parameter, and we will talk more about it after we create the first mesh, and there's a lot of discussion of it in the guide page as well. But if we come back over to our Chimera X session here, if you hover over one of these segments, you can see that it has a number, right? It has the pound sign 2.3. That's Chimera X's model ID. We don't care about that. What we care about is that first number, 380. That is this segment's segment ID. If we hover over this one, it's 381. We can see that the channel itself is 379, and then this micelle segment is 378. You can also see those over in your model panel here by color, and then here's the ID, and you could turn them off and on if you wanted to figure it out that way. I like to just hover. But what we're doing with these parameter here, the segment connection parameter, is we're telling it which segments should be forced to move together. So to put another way, which segments that are touching one another should be forced to be fused to one another. So in this case, as I said, we want the fabs to be fused to the channel, right? We don't want this green fab to be allowed to slip and slide relative to the channel, because we know from biochemistry and from our 3D variability results that this fab should be basically fully attached to the channel. So I'm going to put that in. And the way we type that in is, and it's explained here if you hover it, if you type X and then greater than symbol Y, it means that segment Y is joined to segment X. So basically X is the parent of Y. So you always want to start with your root segment, and this is the one that is kind of everything else is moving relative to. So in our case, the ion channel is going to be our root segment, since we think everything else is flexing relative to the ion channel. And so I'm going to say 379 is greater than 381 to say that 381 should not be allowed to move relative to 379. Put another way, the fab should not be allowed to slip and slide on the ion channel. So 379 is greater than, I already forgot the number, 381. I'll put a comma, and then we're going to do the same thing for the other fab, right? 379 is greater than 380. And then finally, the micelle. And dealing with micelles in 3D flexible refinement is actually somewhat challenging. I'm going to wait until we have generated our first mesh to discuss the challenges inherent in the micelle, but I'm going to go ahead and just say that 379 is also greater than 378. So essentially everything should be fused to this core region, the ion channel itself. So that means the fab is allowed to move relative to the fab, the micelle is allowed to move relative to the fab, but it's not allowed to slip and slide up and down the ion channel, which is kind of what we want, right? We don't want the ion channel to sort of fall out of the micelle. We know that these things should all be more or less coupled to the ion channel. So that's going to be 380 is greater than 378. So these are the segment connections. And this, again, is the entire reason we created this custom mesh, right? We are creating it to allow for this slip and slide. We're creating it to allow 381 to move relative to 380, but not 379. So this is an extremely important parameter, and it's one you want to think carefully about before you submit. Rigid segments is a way of defining which of these segments should not be allowed to flex. And this is another important parameter. If you think that some part of your target is not flexible, then marking it as rigid will sort of help free up some sort of computational space to model flexibility in other regions. In our case, I'm not going to mark anything as rigid. There is some of our work has suggested it might be good to mark micelle as rigid, but I'm going to talk more about that again once we have our first mesh, just so we have something to look at so it's not as abstract. So I'm going to leave this empty. Minimum rigidity weight is a way of kind of encouraging empty space to move instead of space that has map density in it. Again, we find that 0.5 is a pretty good value here, but you could turn it down if you notice that tetrahedra in empty space, in solvent space, are not moving very much. I'm going to go ahead and queue this job. So if we open up the results, we can see it's done a few things. This is just our consensus volume. It's just showing us kind of what the volume looks like. Here is our solvent mask. And so you can see the mask covers the sort of intracellular part, the transmembrane domain. It's got a bulge here for the micelle. And then we cover the fabs as well. The next thing that the mesh prep job does is it hardens the mask. So, you know, in other videos and all throughout the guide, we always emphasize masks must be soft, right? And this is because when you cut through density, if you don't have that soft edge, you get these ringing artifacts in Fourier space, and that really damages your alignment. But in this case, we're not actually modifying any density. We're just using this mask to say, where should I put a tetrahedra? And since it doesn't really matter whether you're putting a tetrahedra in 0.5 or in 1.0, we can harden the mask here. And that just makes the math a bit easier. So then here we show the masked consensus reconstruction. And in this case, you really don't want to be masking out any part. Remember, I mentioned that if the 3D flexibility model can't see part of your volume, it will still be able to see it in the particle images that it's trying to model. And so it will move things where they shouldn't move just to sort of recapitulate, right? You could imagine if we masked out one of these fabs, the model might try to move density from one fab to the other in order to kind of fill those spots in the image. So you want your input consensus reconstruction volume to basically identically match your masked input consensus reconstruction. Now we come down here, and this is the base mesh. So what we're looking at here is each of these colors is a different tetrahedra, and you can see that we have tiled the entire box, and if you were to sit here and count these, you would see that there are 20 tetrahedra on a side. And remember, that's because when we were creating this mesh, we told the job to use 20 tetrahedra to a side. So now what we're going to do is we're going to take this tetrahedral mesh and exclude any tetrahedra that are entirely outside of our mask. So if we look at our mask here and we look at our tetrahedra cells, this tetrahedron, this little triangle down here, would be way out here. It has none of the voxels of the mask are inside that tetrahedra, and so we delete it. And so we end up with a tetrahedral mesh that only has a tetrahedron where we had our mask. And so now we have this trimmed mesh. So we can see that it still follows exactly the borders of the triangle, right? We don't have any kind of half tetrahedra, but all of these tetrahedra contain at least one voxel from our mask. So now if we come down here, we can see that we've loaded our segmentation file and it has the following IDs, which match what we saw in Chimera X. And then we're going to create a mask for each segment to show, we successfully masked out the micelle. Here is the core of the protein, and then each fab. This red fab is a little bit hard to see. But the colors here don't really mean anything aside from just to identify which goes where. And then this is what I was talking about when I said the segments would be expanded to fill the mask. So basically, this just has segment IDs where we actually had density, but we want to fill the mask up so that we know which tetrahedron belongs to which segment. And so that's what this is here. This is the border of that hardened mask, and we've just taken these segments and said, all right, expand them until they either run into another segment or until they hit the edge of the mask. And so that's why if you look at a slice through the center, we see the transmembrane domain or the helices maybe in here, but then it's all micelle there. Here's our two fabs, the micelle and the sort of core of the ion channel. So this is the segmentation of our mask. And then finally what we do is we assign the tetrahedra based on which segment of the mask they're in to a segment of the mesh. And so now our mesh has been split into 4 segments, just like we wanted. We have this core region, we have the micelle, and then we have a mesh for each fab, okay? Finally, we set the rigidity weights. And since we told the job to just use kind of a basic rigidity weight, we didn't set any domains to rigid. We didn't change the rigidity sort of properties. We end up with a low rigidity at the edge, which makes sense, right? This should be more flexible than the part that is touching more protein. And then in the middle, we have a relatively uniform rigidity. And again, the rigidity is kind of how expensive it is to deform a tetrahedra. If a certain tetrahedron has a high rigidity, then that means we tell the model it should prefer not to deform that tetrahedron. Whereas if it has a low rigidity, we can say, it's sort of cheaper, it's easier to deform that tetrahedron. Let's go ahead and inspect this mesh. I'm going to use a tool that I wrote to provide a little bit more detail. You generally don't need to download and inspect your mesh. Usually this is sufficient just to see that everything you did worked. You can also download this PDB here, which will show you the results. But since for this video, I wrote a special tool to sort of provide a little bit more insight into what's actually going on in these meshes. And especially I want to talk about what a fusion means and why that happens. All right. So here is the mesh that we generated, and it can be a little overwhelming to look at first. So I'm going to explain what exactly it is we're looking at here before I start to sort of show some details about what this mesh is actually doing. So if we zoom in, here are, I'm going to bring this up a little bit so we are only looking at a few. Here are individual vertices. And so the way we generate a mesh is we create a set of vertices across the entire box, and then we connect them to form these tetrahedra. And that's what all of these tetrahedra are here. They are the individual tetrahedral cells of the mesh. So when we model deformation, what we're modeling is the movement of one of these vertices in some direction. And so what that means is that if we were to say move this vertex and this vertex closer together. Let's say we move just this vertex to the right. This tetrahedral cell would shrink in this way. And so all of the density contained inside this vertex, which is none in this case, would be sort of compressed along this axis. But the important thing to remember is that this tetrahedral cell, the one below the one I was just pointing at, also uses this vertex. And so it would also be compressed, right? That's the really important thing, is that whenever we move one of these vertices, we are typically moving many tetrahedral cells. We're typically deforming many tetrahedral cells. We're not just deforming one tetracell at a time because they all share these vertices. Okay, so that's what these spheres and these tetrahedra are. I've also added a colored annotation to tell us which mesh each vertex is a part of. Because when we create our custom mesh, if we look at the CryoSPARC image, it looks like these meshes are entirely disjoint, right? That they don't overlap at all. But in reality, they do overlap by exactly one tetra as long as we haven't fused them together. And that's what I'm showing here, which is this vertex is shared by the yellow mesh and by the blue or purple mesh. And so if what that means is this vertex is actually two vertices. If we want to compress just the yellow tetrahedron, but not this blue or purple tetrahedron, then we can move just the yellow copy of this vertex and leave the blue one here. And that is very different from what happens when we have this blue vertex over here, right? This one has to move all of the tetrahedra that are touching it, whereas this is actually two different ones. We can move the yellow and blue meshes independently. And that's because if we zoom out, the yellow and blue meshes are the micelle in blue and the fab in yellow. And we didn't fuse the micelle and the fab. Okay, so it makes sense that we're allowed to move those independently. We want this micelle to be able to flex left and right without worrying about, or excuse me, we want this fab to be able to flex left and right without worrying what the micelle is doing. Okay, but if I turn off, and excuse me while I figure out which one it is, if I turn off the micelle mesh just so we can see what's going on, let's come in here and look at the pink mesh. Okay. So the pink mesh is fused to the yellow mesh and the blue mesh. And that's because the pink mesh is the core ion channel, right? Recall that we took the transmembrane domain and the sort of terminal domain down there, and we said that those should be the core, right? Everything should be fused to those and should not be allowed to move independently. And so if we look here, we can see two important things. First is that I've marked these vertices with the colors, right? They still belong. This vertex sort of belongs to, or another way to think about it is that each of the yellow, pink, and blue meshes have use this vertex or have a copy of this vertex. But they're connected here because yellow is fused to pink and blue is fused to pink. And so if we ever move this vertex, we have to move all three meshes that use this vertex. That is the really critical thing that we're doing when we perform these fusions. The other thing to note here is that even though there are sort of interspersed yellow and pink tetras, they never overlap perfectly. And that's because they're fused. It wouldn't make sense for us to fuse the yellow and pink tetras and then have a copy of the yellow in there because they must deform in the same way. And so what we do when we mark a segment as a root or as a parent of another segment is we say any tetrahedra that belong to both of the yellow and pink mesh in this case, replace it with just a single tetrahedra that belongs to pink. And then any vertices that are used by the yellow and pink meshes must move together. So just to review, what we're looking at here is the yellow mesh, which in our case belongs to one of the fabs, and the pink mesh, which in our case belongs to the ion channel. And since we have fused those segments, they cannot move independently. Any vertex that is shared by both yellow and pink must move the same for both meshes. So for instance, if we look at this triangle here in the kind of front view of our camera, if we want to move this tetra so that this vertex is closer toward the center of this tetrahedron, we necessarily must move the pink tetrahedra's vertex to be in the same position. Here I've shrunk the tetrahedra just so it's more visible what is going on, but remember that these are in fact connecting the vertices exactly. So if we move this vertex up here for yellow, it must move there for pink. And what that means is that any deformation that the fab has must be matched by a deformation the ion channel has, which makes sense. That's what we want. We don't want the fab to be able to float up and away, which is what would happen if we allowed the yellow vertex to move up here to sort of compress up this way, but kept the pink down here. We want them to be attached to each other. Okay. So now let's zoom back out and compare that to the green mesh, which is our other fab here. And you can see from this view where we kind of line up all the vertices along this way that the green and yellow meshes do have overlap. And that's because just like the fab and the micelle, we want these green and yellow meshes to be able to move independently. So when this part of the fab moves left and this part of this fab moves right, what can happen is the yellow mesh can take its copy of this vertex to the right to match the deformation we see here. And the green mesh can take its copy of this vertex left to match the deformation we see here. And that will also bring with it all of these tetrahedra. That's why they overlap. Each of our meshes has a separate kind of copy of this region of the map that it's allowed to deform. But now, if we look down here, this part of the map was probably within our fab segment. However, if we look closely, it is all fused to the pink segment. And that makes sense, because right here is where we start to say, this is too close to the core of the ion channel. We want this part to be fused to the ion channel, which means any tetras in here that belong to the fab and to the ion channel are going to get assigned to the ion channel, and then we're going to fuse these vertices together so that they can't move independently. But this is a really important point. Look at this vertex. All of these meshes, all four of our meshes, right? Yellow and green are our fabs, pink is our ion channel, and blue is the micelle. This vertex, even though it is used by all four meshes, can only ever be in one position, okay? And that's because it is all fused to this pink mesh. So even if green and yellow want to move it separately, they can't, because they have to be in the same position as pink. And even if the micelle wants to move somewhere else, it can't, because it has to be in the same position as the ion channel. And this is really important because let's say that we had marked the micelle as rigid, right? Let's say that we had said, I don't want my 3D flexible refinement model to try and figure out what's going on with the micelle. Let's just treat it as a rigid object. Well, if it was rigid for the micelle, then it wouldn't be allowed to move. Or it would be allowed to move, but it would be very expensive, right? The model would have to really be explaining a lot of information to move it. So it would become very challenging to move purple's copy or blue's copy of this vertex. But the problem is pink's copy of this vertex must be in the same position as purple's copy because they're fused. And what that means is also the fabs would have to have the same position as the micelle. And so this is what I was saying when even if you have a region that you want to mark as rigid, which we may have wanted to do for the micelle, you need to be very, very careful because by marking the micelle rigid, we would have actually marked this vertex for all of our meshes rigid. And, you know, that may not sound like a huge problem, but let's consider our 3D variability results again. Remember that we saw the transmembrane domain is moving up and down within the micelle. And if we mark the micelle as rigid, but then fuse it to the transmembrane domain, that movement would not be allowed to happen. All of those edge vertices would be fused to the rigid vertices of the micelle, and so they wouldn't be able to move because the micelle wants to hold them rigid and they must occupy the same position. So this is the really tricky part of creating a custom 3D Flex mesh, is figuring out what do we want to fuse together, what do we want to keep separate, and what do we want to mark rigid. And there's a lot to consider when you're making these decisions, and I've written a lot more about it in the guide. But generally, our advice would be to try a couple fusion strategies and see what works best for you. So for instance, in one case, you might try to hold the micelle rigid and do a fusion sort of as you'd expect, fuse it to the TMD, fuse the TMD to the fabs independently, but don't fuse the fabs together, kind of like what we've done here, and see how that works. You could try one with the micelle rigid and one without the micelle rigid, and then you might try something a little more surprising based on the biochemistry, right? We can see that the micelle here overlaps with this fab. And so maybe you mark the micelle as rigid, but fuse it to the fab instead. And then you fuse the fab to the transmembrane domain, and then the transmembrane domain to this other fab. And that would give you the same relative topology in the ion channel and fabs, right? Where the fabs would each be fused to the ion channel, but not to each other. But the important thing is the micelle will be fused to to this fab here. And what that might do for you is it might let the transmembrane domain over here move up and down relative to the part over here, even though the micelle is still rigid over here, because the micelle and the transmembrane domain are not fused. The micelle would only be fused to the fabs. So it might be harder, if you did that, it would be hard, the micelle here would be fused and rigid to this, which would hold this interface rigid, which would then hold sort of these vertices rigid. Anything shared by yellow, pink, and blue or purple would be held rigid. But over here, where you just have, for instance, pink, green, and purple, these would not be rigid, even if the micelle is rigid, because this fusion between pink and purple would not be happening. So I hope that this video has given a little bit of insight into how we recommend that you design a custom 3D flexible refinement mesh. The important steps that we covered are how to think about the mesh, what it's trying to do, which is to sort of impose this spatially smooth deformation on the deformation model instead of allowing individual voxels to move sort of willy-nilly. We covered the strategy behind what you might want to segment out from each other and what you might want to sort of combine into one segment, with the idea being that anything you expect to either have a different rigidity or anything you expect to move sort of slide past each other or move away or toward each other, you might want those to be in separate segments. And then we discussed a lot about what it means to fuse segments and sort of different strategies for how you might perform these fusions and when you might want to leave things unfused, and especially how that interacts with rigidity. And to summarize that part of the video, I would say you want to perform fusions in a way that retains flexibility you care about, while being careful not to unintentionally restrict the sort of edges of your segments. So in this case, we talked about how we definitely want the fab and ion channel segments to be fused together at their border so that the fabs don't float off away. But we also talked a lot about how if we impose rigidity on the micelle, it becomes challenging to ensure that our transmembrane domain is still allowed to flex in the way that we know it does based on our 3D variability results. As always, there are a lot more sort of figures and a lot more written discussion of these interesting topics in the guide, and the discussion forum remains a valuable resource if you have any additional questions after watching this video. Good luck generating your 3D flexible refinement meshes.